Welcome back to this session. Today in this session, we'll be finding moment of inertia of an unsymmetrical eye section. So as you can see, I've already drawn the diagram. So before we start solving the numerical, let's read the question. Determine the moment of inertia of an unsymmetrical eye section having the following details. Top flange, so this is my top flange here, is given, its dimension is given 160 mm into 12 mm. So this is my top flange and its width is given 160 mm and its depth is given equal to 12 mm. Right? Similarly, bottom flange is equal to 240 mm into 12 mm. So this is my bottom flange here. So this is equal to 240 mm and its depth is equal to again 12 mm. Right? So as you can see, this top flange and bottom flange, they are not equal. The dimensions are different. So that's why this kind of eye sections are known as unsymmetrical eye section. Okay, so now let us see the dimension of web portion. Web, for this is the orange section in here, is my web portion and its dimension is given 200 mm into 10 mm. So this 200 mm here is clearly my depth, 200 mm, and its thickness is given equal to 10 mm. Right? So this is the question that has been given, and for this we need to find moment of inertia about two axes. So the two axes here will be moment of inertia about ix axis. Let us say that ix axis is running somewhere from here, x axis, and let y axis run from here. This is my y plane, right? So now here is my centroid G, but we do not know at what height this centroid G lies. So we need to find that as well. So let us see how we can find all this. So first, they have asked us to determine moment of inertia of an unsymmetrical eye section. So we need to determine moment of inertia about both the axes now. So we will first find moment of inertia about x axis. Okay, so first we will say x axis, then second we will find moment of inertia about the second plane, that is y plane. So now how do we find moment of inertia about ix? Before we start, let us make this section into three sections, divide this section into three sections. Let this top flange be equal to first section, number 1, this web portion second, and the bottom flange be the third section, right? Now in yesterday's question, if you compare to yesterday's question, for the yesterday's question, to find ixx, we converted the symmetrical eye section into a hollow rectangular section because that was possible since both the flanges were of the same dimension. But in this case, we cannot make this unsymmetrical eye section into a hollow rectangular section. So hence we have to solve using a parallel axis theorem. So in here, since I have three sections here, so my ixx will be equal to moment of inertia about the first section, that is web, that is my flange portion here, ixx1, plus moment of inertia about my web portion, that will be moment of inertia about the web portion will be Ixx2 plus my moment of inertia about the third section, that is the bottom flange, and that this is Ixx3. Now I have to find for each how much will be my Ixx1, Ixx2 and Ixx3. Since my Ixx1, 2 and 3, all three of them are running parallel with the XX axis, so if I find my Ixx1, for this Ixx1 I have to apply a parallel axis theorem. So the parallel axis theorem here will be equal to IG1 plus area 1 H1 square. So this is my parallel axis theorem to find moment of inertia about the first section, that is this flange portion, right? So if I say this IG here, G here represents the moment of inertia about the centroidal axis. This centroidal axis Ixx1, centroidal axis about this XX plane and section 1, right? So my IG1 here be equal to BD cube by 12 plus area 1, area of this flange portion, into its height 1 square. So this will be my moment of, this is how we can find moment of inertia about this first plane Ixx1, which is Ixx1, right? Now we know that from the given question B as well as D is given. Area also we can find. Now how do we find this height H? How do we find H1? To find H1 we need to first find Y bar. Y bar will be equal to A1 Y1 plus A2 Y2 plus A3 Y3 divided by the addition of all the three areas. So this Y bar here is my this distance from here till this section here. So this will be my Y bar, and I'm trying to find how much is my Y bar by using this formula here. So after I find my Y bar, I can easily find my height H1. My height H1 will be equal to Y bar minus Y1. Now let us first find this Y bar. Let us find Y bar, then I'll let you know what is Y1, since we have to find Y1, Y2, Y3 all in this section here. So I'll show you each one how we can find all these values. Now let us first find area 1. Area 1 for the first section number 1 here will be equal to 160 into 12. So this will be equal to, let us solve in the calculator, 160 into 12 is coming equal to 1920. So it is equal to 1920 mm square. So this is my area 1. Now how much will be my area 2 for the web portion? So my area 2, A2 will be equal to 200 into 200 is the depth of this web portion into its thickness. It's 200 into 10. So this is easier. This will become equal to 2 into 10 raised to power 3 mm square. So this is my area 2. Area 3, A3 will be equal to, for the bottom flange, it will be equal to 240 into 12. Let us solve this in a calculator again. 240 into 12. So this is coming 2880. 2880 mm square. So now we found A1, A2 and A3. So A1, A2 and A3 we found. Now let us see how we can find Y1, Y2 and Y3. So let me first find Y1. Y1 will be equal to, so now for Y1 I have to look at this first section that I have divided, that is this top flange, and I have to go in Y direction. How is the Y direction going? It is going vertically like this, right? Vertically, it is going vertically. So I have to look in a vertical direction. I'm gonna look from top, from this top I'm gonna go down till here. So before I go from top to down, I have to look at this first section, since I'm finding Y1 for the top flange, right? So my Y1 here is equal to, only for the top flange you will look, its depth is given 12 here. So my Y1 will be equal to 12 divided by 2. So this will come 6 mm. This here means that I'm finding this much portion, this much, only this much. This is my Y1, right? Now if I am to find Y2, I need to find for this web portion here, web portion, which means I need to come from all the way from top till here, right, till here. So what I'm gonna do, I'm gonna add 12 of the top flange plus half the height of my web portion. The total height of web is 200 divided by 2. So this will come equal to 112. 112 mm, right? Similarly, now I have to find Y3. So if I am to find Y3, I need to come from this top flange till my bottom flange, but for the bottom flange it will be only half of the bottom flange. So half of this bottom flange, which will be till this portion here. So I need to find this height. This is my Y3. This is my Y2. So I need to find this height. Now how much do I need to cover? I need to add this total depth of my top flange plus total depth of web and half depth of bottom flange. So this will be equal to Y3 will be equal to, the total depth of top flange is 12 plus total depth of web is 200 plus. Now I only need to go for till half the depth of this bottom flange. So half will be 12 by 2, which is 6. So how much am I gonna get? 218 mm. So this is my Y3 here for the bottom flange, or the third section, as I have divided here in the diagram. So you have found all the values of A1, A2, A3 and Y1, Y2, Y3. Now putting this in Y bar to find Y bar will be equal to, area 1 came out to be 1920 into Y1 is 6 plus area 2 is 2 into 10 raised to power 3 into Y2 is 112 plus area 3 is 2880 into y3 is 218 divided by, now total area. So area 1 is 1920 plus 2 into 10 raised to power 3 plus third area is 2880. So if we solve this in a calculator, let's see how much you will get. So I have 1920 into 6 plus 2 into 10 raised to power 3 into 112 plus 2880 into 218 divided by the total area, which is 1920 plus 2 into 10 raised to power 3 plus 2880. So this is coming equal to 120. It is coming equal to 126.9. So it is coming 126.9. 126.9. So approximately I can say this value is 127 mm. I'm converting and making this into a whole number and not leaving it in a decimal points, so that it will be easier for me to find all the values, and it will not be in a decimal point but it will be in a whole number. So now I have found my y bar. That means from this top flange till this portion where my centroid is lying, my y is coming equal to 127 mm. So now we know this height. Now let us find h1. Since we require h1 here, so how much will our h1 be? h1 is equal to y bar minus y1. Okay, so what I'm gonna do, I'm gonna directly put this in this formula here, and then I'm gonna find it. Okay, I have my y bar also, and y1 also I have. Y bar came equal to 127 and y1 is equals to 6 mm. So similarly, to find h2 will be equal to again y bar minus y2. Similarly, h3 will be equal to y bar minus y3. So this is how you find h1, h2 and h3. Now let me find ixx1. So therefore my ixx1 will be equal to bd cube by 12 plus area 1 into h1 square it was. So in place of h1, I'm gonna put this value here, which is equal to y bar minus y1 square. Now if I put all its value for this top flange section 1 here, its b is equals to 160 and d is 12. So let us put here b is equals to 160 and its depth is 12 cube by 12 plus how much is our area 1? Area 1 was 1920 into how much was our y bar? Y bar was equals to 127. So 127 minus how much was our y1? Y1 was equals to 6. So y1 was equals to 6 a whole square. Now let me solve this in a calculator again. I'll open the bracket. 160 into 12 cube by 12 plus, let me open the bracket here again, 1920 into 127 minus 6 the whole square and bracket close. So I'm getting equal to 28.13 into 10 raised to power 6. So this value is coming 28.13 into 10 raised to power 6 mm raised to power 4. So this is my Ixx1. Similarly, I want to find Ixx2 also. Now I have to find this value here, Ixx2, right? So this Ixx2 will be for my this orange portion here, which is my web portion. So similarly for this web portion Ixx2 also I need to use parallel axis theorem. So here it will be Ixx2 will be equal to BD cube by 12 plus A2 into Y bar. Now my H2 is equal to Y bar minus Y2, its whole square, right? So how much is my B here for the web portion? B is equals to 10 and its depth for the web portion is 200. So my B here is equals to 10 and its depth is 200 cube by 12 plus how much was my area A2? A2 was equal to 2 into 10 raised to power 3. So area was 2 into 10 raised to power 3 into Y bar was 127 minus Y2 was equal to 112. So it was equal to 112 the whole square. So let us solve this. Let's see how much we get this again. 10 into 200 cube by 12 plus 2 into 10 raised to power 3 into 127 minus 112 the whole square. So this is coming equal to 7.116. So since I have a 6 here, I'm just rounding it off and making it 7.12 into, so I have 7.12 into 10 raised to power 6 mm raised to power 4. Similarly, for the third section, which is the bottom flange, it will be Ixx3 and I have BD cube by 12 plus area 3 into Y bar minus Y3 the whole square. So this will be giving you equal to, how much is my B and D for the bottom flange here? The third, B is equals to 240 and D is 12. So my B is 240 into D is 12 cube by 12 plus how much was the area? Area 3 was 2880. So I have area 3 as 2880 into Y bar was 127 minus Y3 was equal to 218 mm. So y3 is 218 mm square. So let us solve this in a calculator again. How much it comes? 240 into 12 cube divided by 12 plus its area 2880 into h square, which is 127 minus 218 square. So this is coming equal to 23.88 into 10 raised to power 6. So this is coming equal to 23.88 into 10 raised to power 6 mm raised to power 4. So my total moment of inertia about Ix axis will be equal to Ixx1 plus Ixx2 plus Ixx3. So about Ixx1, moment of inertia was equal to 28.13. I have 28.13 into 10 raised to power 6. This is Ixx1 plus Ixx2 was 7.12 into 10 raised to power 6 plus Ixx3 is 23.88 into 10 raised to power 6. So let's add them all. Adding them all, I'll be getting plus answer. This last answer is my Ixx3 plus Ixx1, which is equal to 28.13 into 10 raised to power 6 plus Ixx2, which is 7.12 into 10 raised to power 6. So I'm getting 59.13 into, I'm getting 59.13 into 10 raised to power 6 mm raised to power 4. So this is my moment of inertia about Ixx. Now second, I want to find moment of inertia about y axis. Now to find about y axis, I can directly find it. Iyy will also be equal to Iyy1 plus Iyy2 plus Iyy3. If I want to find moment of inertia about Iyy, which is this plane, y here, yy here. So to find Iyy about this first section, so it will be equal to dB cube by 12, dB cube by 12, then for the second wave portion dB cube by 12, and for the third dB cube by 12, since it is not running parallel with any of the plane. This section is not running parallel with yy plane, so I can directly find it by using the formula dB cube by 12. So here will be equal to dB cube by 12 for the first section, that is top flange, and for the web portion dB cube by 12 again, plus for the bottom flange dB cube by 12. So how much is my dB cube by 12 for the first top flange? My depth was equal to 12 and was 160 cube by 12 plus again for the web portion here, my D is 200, B is 10. My D is 200 into depth is 200 into B is 10 cube by 12. And for the third flange portion, my depth here is 12 and its width is 240 cube by 12. So if we solve this, this will be coming equal to, in a calculator, 160 cube by 12 plus 200 into 10 raised to power 3 divided by 12 plus 12 into 240 cube by 12. So my moment of inertia about IYY is coming equal to 17.94 into 10 raised to power 6 mm raised to power 4. So this is my moment of inertia about IYY axis, and this here is my moment of inertia about IXX axis. You can also solve moment of inertia about symmetrical I section in this manner as well. You can solve moment of inertia of a symmetrical I section in this manner. You can find IXX by dividing the symmetrical I section into section 1, 2 and 3 and find moment of inertia about all the 3 sections and find it in this manner. But you cannot find moment of inertia of an unsymmetrical I section as you have found moment of inertia of a symmetrical I section for IXX axis. I hope the numerical is clear today. Tomorrow we'll be solving some more numerical based on moment of inertia, and the section that we're going to solve tomorrow will be T section. So see you tomorrow.